All right, welcome back to your next lesson. This is a good one. We're doing 8.2, which is connecting position, velocity, and acceleration of functions using the integrals. I will do 8.2. I'm actually not going to do 8.3 for those of you who are looking at your chapter 8 stuff. I think this will be sufficient for what we need to get through. So it'll be lesson 2 on the Flamingo math stuff. So, but it's 8.2 in the calculus standards. All right, and this is a really good review of what we had done before, and a lot of it, honestly, we talked about, but this just kind of makes it official. We've officially talked about it now. All right, so particle motion problems deal with motion along a straight line. This includes horizontal and vertical motion of a falling object. It's important to note that the motion meant the particle was moving along an axis, not along the graph of the function. Now it's possible for us to work in two directions. For example, if an object is traveling in a straight line, then its velocity can be expressed as the integral of acceleration. Now we will focus on getting a better understanding for how to model motion problems that will appear in the AP Calculus exam. All right, so the net change is actually what you've been doing. That's just, you're from A to B, blah, blah, blah. And we're going back to the whole area thing, and this is totally leading us in the direction that we're going to be going. So this is when you do the net change, you're not considering what's positive, what negative. It's already just kind of taking care of that for you. So, like, let's say you have this as your graph. So this is the graph of the velocity. Most of your graphs are going to be the graphs of the derivatives, not the graph of the original function. So when given an object's velocity, in a question stem is asking about the object's position, we need to understand what definite integral is necessary to respond to the prompts. Okay, so displacement, what's going to be happening when you take the integral? Area 1 and area 3, remember, are positive because they're above the x-axis. Area 2 is negative. So when you take just the integral from A to B, you'll be doing whatever this area is minus whatever this area is plus whatever this area is. It just naturally happens. However, now you can be asked, what's the total distance traveled? If it's the total distance traveled, you're doing the absolute value of the velocity. So the A sub 1 is fine. It's already positive. But you would have to do the opposite for A sub 2. So you would have to do whatever A sub 2 is, but make it positive, and then you would add on your A sub 3. So it's just, you treat the negative part differently. And then for the actual position, you have to add in the initial position, because remember, this may not take that into consideration. And like I said, all these things we've kind of touched on. Like, it's not... This shouldn't be totally new, but you are going to have some word problems. Okay, so if you're given that S of 0 equals 4, so your initial condition is 4, find the displacement, total distance traveled, and position on 0 to 10. So we're given this graph, and of course my thing went away. Okay, we're given this graph, and we know that this area up here is 18. And this area down here is 12. We know it goes from 0 to 10, and we know our initial position is 4. All right, so if we were doing the displacement, the displacement would just be the integral. So the integral from 0 to 10 of v of t would equal 18 and then plus a negative 12, or we could just do minus 12, and it would be 6. So the displacement, it'll move 6 to the right because it's positive. So that's how far it is in the end. So it's gone to the right 18, to the left 12, so it ends 6 to the right. That's what your displacement is. And then the next we have total distance. That's this next one. So this is the total distance. That's the part that the particle traveled. So this one is the absolute value of the velocity function from 0 to 10. So you would do, I forgot dt on this one, and actually I forgot on this one too. My bad. So the total distance traveled, you would have 18, and then it travels another 12 meters. So it's a total of 30 meters. So even though you're 6 to the right of where you started, you've traveled 60 meters total. And then the last thing is the actual position. So the position on 0 to 10. This is where we consider position. This is where we consider where we start. So we start at 4, and then you consider your displacement, which would be the 0 to 10 of v of t dt. So you'd have 4 plus your 6, which is 10. Okay, so that's just kind of showing the 3 different things with our graph. All right, example 1, this is a review. All this is from stuff that we've done before. All right, so the graph of the right represents the velocity, which means it is the graph of the derivative of the particle that's moving along the x-axis. So we have a left and right moving. We're going from 0 to 8. And it's measured in inches per second. Okay, for what interval of time is the particle moving to the right? Justify your answer. All right, so it is moving to the right when our velocity is positive. So the 2 time spans when it's positive. So it's positive from 0 till we get to 3. At 3, it's changing directions. And then it's going left, 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 left. And then we're changing to positive. So from 7 to 8. Those are the 2 times when it's moving positive. And the justifying, this is where your v of t is greater than 0. Okay, for B, on what intervals is the particle slowing down? Justify your answer. All right, so this is that whole, like, the signs are different, the signs are the same thing. So when it's slowing down, that means your signs are opposite. So we need either a positive slope and, okay, this is actually wouldn't be, this is a non-example, because you have a positive slope and it's a positive value. So that's not going to be it. So we need opposite signs. All right, so here we're slowing down it's got a negative slope and it's positive. So that would be an interval right there, but not when it changes to negative. So it looks like from 2 to 3. Actually, let me do the other notation. So 2 less than t less than 3. Because, so 2 to 3. So the velocity is positive. And acceleration is negative. Acceleration, or the slope of v of t, is negative. And then we actually have another one. So this one is negative, negative, not it. This one we have a slope of 0. Here we have a positive slope, but it's in the negative. So we have another one from 6 to 7. And then it changes to positive, positive. So from 6 to 7, because the velocity is now negative, And the acceleration is positive. So the slope of v of t is positive. Okay, so when they're opposite, that's when it's going to be slowing down. All right, C, when is the particle stopped and changing directions? Okay, so stopped and changing directions, that's when our positives become our negatives or our negatives becomes our positives. So we have two places where t is 3 and where t is 7. Because v of t equals 0. And then finally, on what time interval is the acceleration 0? Justify your answer. That's when your slopes are 0. So when this is constant. So our first place where this is constant. Sorry, I'm trying to tell what you can see. So the first place where this is constant is here from 1 to 2. And the next place is from 4 to 6. Because CA, oh my goodness, I can't write today. Is constant. Okay, so hopefully that's all review for you. You're like, oh yeah, I remember doing that. Hopefully it brings back fond memories. Okay, this chart's a little tricky. So the city bus accelerates as it leaves one stop, then decelerates as it comes to another stop. The chart below measures the velocity v given in miles per hour between each stop. So these are the time in minutes. We're going on 5-minute intervals here. And it goes, so our velocity, it's speeding up, slowing down, speeding up, slowing down, speeding up, slowing down, so on and so forth. Because just what the velocity is, the instantaneous velocity at each place. So we're supposed to find the distance in miles the bus travels between each interval using the trapezoid rule. Okay, so this is a little bit tricky. First of all, we're starting at 0. Our first distance is 0. So we have to use this info to figure out what goes here. So if we use the trapezoid rule, remember that's 1/2 the height and then base 1 plus base 2. Yep, not going away. So we have 1/2. Now the height, all of our heights are 5. 5, 10. Oh, just kidding. No, they're not. That one's 10. Okay, so for this first one we have 1/2, and then this height is 5. And then B1 and B2, we would have 0 and 18. All right, so we have 0.5 times 5 times 18, and we get 45. Oh. Oh, just kidding. Okay, I know I did wrong. This is 5 minutes out of 60 minutes. Because this is in minutes, but we need to do miles per hour. There we go. That would be miles per minute. Okay, try again. So 0.5 times 5 divided by 60 times 18. We get 0.75. There we go. So it goes 3/4 of a mile between minute 1 and minute 5. All right, so the next one. So this one would be 1/2 And then from 5 to 10, we're going 5. So this time I'll get it right and do 5 over 60. And then it would be 18 plus 6 for our bases. Okay, so we have 0.5 times 5 divided by 60 times 24. So you get 1. So then it goes a mile. Okay, so then between 10 and 20, we have 1/2. It's going 10 out of 60 hours because it's 10 minutes out of 60. And then it would be 6 plus 32. So 0.5 times 10 divided by 60, or 1 divided by 6, times 38. We get 3.166. I guess we should do 3 decimals. Okay, 3.167. So on and so forth. This, hopefully you get the idea using trapezoid rule. Good review of trapezoid rule. It's time to be reviewing anyway. So this one, you would do it, you should get 1.5. This one, you should get 1.667. This one, using trapezoid rule, you get 4. This one, you get 4.25. And this one, you get 0.917. Alright, so that's the distance in miles the bus travels between each interval. Now we need to find the total distance that the bus traveled in 60 minutes. So if you were going to do that, what you would do is you would just add all these together. So you'd have 0 plus 0.75 plus 1 plus 3.167 plus 1.5 plus 1.667 plus 4 plus 4.25 plus 0.917. You should get approximately 17.249 miles. Just by adding all those together. So that's just doing it in chart form. You're usually going to see it in graph form. But it's good to just kind of have a visual of what you're doing. All right. Next page. So I actually like all these examples. Sorry, bear with me. It's good for you. Alright, some motion problems will require you to find the actual position of an object or particle at a given point in time. Remember that you'll need to use initial conditions in order to find an actual position, since the definite integral only provides the change in position of an object. Okay, so example 3. We have an object moving in a straight line with that velocity. We're going to need that. Meters per second, where t is in seconds. At t equals 5, the object's distance from the starting point was 12 meters in the positive direction. That will actually become our initial. Okay, for A, it just says write an integral expression that will compute the object's position at t equals 10 seconds. So it doesn't mean we have to figure it out quite yet. We'll have to do that in part B though. So an integral expression that will compute the object's position at t equals 10 seconds. So we already know what it was at 5. We already know that it was 12. So at t equals 5, we were at 12. And then we're going to add on the displacement. So our displacement would then be the integral, not from 0 to 10, but from 5 to 10. Because we already know what happened from 0 to 5. So from 5 to 10 of v of t, which remember v is your derivative, dt. Okay, and then use a graphing calculator. Hope you guys are able to get one somehow, whether it's using that program or whatever, to find the actual position of the object at 10 seconds. Alright, so we'll have 12 plus, and then this is where you use your calculator. It is super cool that you can just go math and then number 9. I always think that's a little inappropriate, the FNINT, whatever. If it helps you remember, awesome. And then we're going from 5 to 10 of the square root of 3. Now it's going to be x minus 2. And you do have to remember to put in that dx so it knows how to integrate it. All right, so you should get 22.50886819. Add 12 to it. So you get the answer of 34.509. And then this would be the position, so it's meters. All right, there's that one. Okay, example 4, also a good one. You have a particle moving along the x-axis with that velocity. All right, formulas are good to remember. Measured in meters per second after t seconds with an initial position of s of 0 equals -3. So we're starting in the negative. Determine the displacement of the particle on the time from 1 to 7. All right, so we want our displacement. It doesn't say where it's going to be or anything like that. It just wants the displacement. So displacement from 1 to 7 of -t squared plus 7t minus 10 dt. I'm going to cheat and use the calculator. You could totally do that one by hand. But I'm going to cheat for now. Go down to number 9. Scooch this up a little bit. Alright, we're going from 1 to 7 of -x squared plus 7x minus 10 dx. What did I do? Oh, I haven't done that error in a long time. Okay, so we get -6. This is actually the displacement. We don't need to bring in -3. We don't need to have where we initially started. It's just -6 from where we started. So what is the total distance traveled by the particle on the time from 1 to 7? All right, so here's the tricky part on this one. We need to know if it ever changes directions, if it ever goes through 0. So I want to know, where does it equal 0? And you could do this by a graph on your calculator and look at it, but this one's pretty nice to do by hand. You can multiply everything by -1. So 0 equals t squared minus 7t plus 10. And this one's actually factorable, and that's why it's not bad. So two numbers that multiply to 10 add to -7, that would be -2 and -5. So when t is 2 and when t is 5. So the total distance traveled from 1 to 7, t equaling 2 and 5, 2 and 5 are both inside that interval. So we're going to have to consider 3 different pieces, like from 0 to 2, 2 to 5. I missed something. 0 to 2, 2 to 5, oh, and then 5 to 7. So there's 3 different pieces being broken up by these two x-intercepts. If you think about it, this is a parabola opening down and crossing over twice. All right, so our 3 pieces, we're going to have to add on. Now, this is a parabola opening down, so chances are it goes negative, positive, negative. I'm just going to do this. So I'm going to do the absolute value of the integral from 1 to 2 of v of t dt plus the absolute value of the integral from 2 to 5 of v of t dt, and then the absolute value of the integral from 5 to 7 of v of t dt. And then we'd have to evaluate each of these. This one, if you do it in your calculator or do it by hand, whatever, you get negative 22 over 12. So we would do the absolute value of that because this piece is under the x-axis. This piece is over then because it's a parabola, so it goes under, over, under. So this one you get the absolute value of 9 over 2 plus, and then this one will have the absolute value of negative 26 over 3 when you evaluate it. So you add all those together. Like if we made a common denominator of 12, we'd have, oops, not negative. I'm taking the absolute value out too. So 22 plus times 6 would be 54. Plus, this would be times 4, you get 104 all over 12. And actually the answer is 15 feet. So in this particular problem, they did tell us the initial position was negative 3, but we never had to use it. So just kind of how it is sometimes. We could have had to, but we didn't. All right, let's keep going. Keep chugging along. All right, example 5. Suppose you're driving in traffic behind a large bus at 66 feet per second, 45 miles an hour. When you finally get a chance to pass, you step on the accelerator, giving the car an acceleration of a of t equals blah, blah, blah. So this is our second derivative, where a is measured in feet per second and t is measured in seconds. How fast are you going 16 seconds later when you have passed the bus? All right, so our initial velocity is actually the 66 feet per second. That's how fast you're going before all this bus passing happens. So that's v of 0. All right, so v of t would equal the integral of a of t dt. So v of t would be the integral of 4 over the square root of t dt, which we could write as the integral of 4 and then t to the negative 1/2 because it's upside down dt, which taking the integral you'd have 4 and then t to the positive 1/2 and you'd divide by 1/2 and then you'd have a plus c. So divide by 1/2 means you multiply by 2. So you'd have 8 and then t to the 1/2 as radical t plus c. And we know our initial velocity is 66. So v of t equals 8 radical t plus 66. Okay, so that is our velocity function. How fast are you going 16 seconds later? That's when t is 16. So v of 16 equals 8 times the square root of 16 plus 66. So you have 8 times 4 plus 66. 32 plus 66 will be 98, and it would be feet per second. We're not doing miles per hour. Okay, so that we used our velocity. Now the B asks, how far did you travel during that time? So we're going to take our velocity. We want to figure out how far we went in the first 16 seconds. So that would be the integral from 0 to 16 of, this would be the absolute value of your v of t. Okay, and then v of t being 0 would only happen at 0 because, oh, that's a lie. Yeah, okay. No, that's not a lie. Okay, so from 0 to 16 of the absolute value of v of t. All right, so we have from 0 to 16 of, where's our v of t? 8, and then t to the 1/2 plus 66. And when would that equal 0? That would be something we would need to consider. Let's just see what the graph looks like real quick. Let's see, we have 8 square root of x plus 66. Let's just use Zoom Fit. We'll cheat. I usually like to use Zoom Fit, but okay, yeah. It said when t is 0 is when it's 0. You can confirm that with the table too. You can really do it by hand also. Okay, so all this is arrow when it's less than 0. All this is positive. So we don't have to worry about breaking it into two pieces. Okay, so we would do the absolute value of this, but it's positive, so I'm not worried about that there. So I'm going to do, this would be 8, and then t to the 3/2 over 3/2 plus 66t from 0 to 16. So times 2 is 16 over 3. So 16 over 3, t to the 3/2 plus 66t from 0 to 16. Alright, plugging 0 in we get 0, but plugging in 16, 16 over 3, and then 16 to the 3/2 plus 66 times 16 minus 0, just to put it there, you end up with 1024 over 3 plus 1056, so approximately 1,397.333 feet. Alright, so that's how far you traveled during that time. Okay, C then asks for your average velocity. That kind of goes with what we're doing. So velocity, or what we were doing before. Velocity is in feet per second. Here in this case it would be, because we have feet and we have seconds. This velocity, the how far you traveled, is in feet. So if we're going to do feet, and then it's for 16 seconds, you just take your 1397.333 feet and divide it by however many you have, which is what you were doing yesterday. And you get 87.333 feet per second. And that's your answer. So to get the average, you just divide by how many you have, which is what you always do to get your average. All right, example 6, and I do want to do example 7 also. Example 7 is really good. You'll love it. All right, so example 6 says you drop your calculus book from a window 48 feet above the ground. That's so sad. How long will it take your book to reach the ground? Okay, so this is your gravity problems where your acceleration is negative. Since we're doing feet, your acceleration would be negative 32. So use this one. I think you have a couple on your homework that use the acceleration. So A of t would be negative 32. And your initial velocity is 0. Initial velocity. equals 0. So how long before it reaches the ground? All right, let's figure out our velocity using our acceleration. So v of t would equal the integral of your a of t dt. So that equals negative 32t plus c, and then our initial velocity is 0. So v of t equals negative 32t. All right, good to know. So now we need to do our position function, which I'm going to use s. Hopefully it don't look too much like 5s. All right, so our position function would be our integral over velocity function. So that's going to be negative 32t squared over 2, and then we have plus c. So we have negative 16t squared plus c. It's 48 feet above the ground, so that's actually where the c comes in. So s of t would equal negative 16t squared plus 48 feet. There's our position function. Alright, so position function then would tell us when we reach the ground. You reach the ground when your position is 0. So we're going to take this position function and set it equal to 0. So 0 equals negative 16t squared plus 48. So 16t squared equals 48. T squared equals 3. So t would equal the square root of 3, which is 1.732. Oh, seconds, right? Yeah. We started at feet per second. All right, and then what is the velocity of the book at the instant it reaches the ground? So this would be our velocity function, the square root of 3. So this is v of radical 3, which is negative 32 times the square root of 3. We would get negative 55.426, and this would be feet per second. Not bad to figure out after you'd figured all that other stuff out from part A. Alright, if you have any questions, let me know. You guys did a great job of asking questions yesterday. It was kind of fun, actually. Actually, just do calculus. Okay, example 7 is awesome. I think it's a great one for putting all these pieces together. I know this is a long video, so thank you for bearing with me. It still isn't as long as the class yet. So a particle moves along the x-axis, so its velocity at time t for 0 to 15 is given by this function. Okay, all this just kind of make sure we're all clear on what's going on in this graph. So at t equals 0, x is 4. So that means your initial position is 4. Alright, so we have initial position at 4. The velocity is 0 at t equals 3. So at 3 we're crossing. T equals 9 we're crossing. And then t equals 13 we're crossing, which I would have guessed anyway, but now it's confirmed. The graph has horizontal tangents at t equals 6 and t equals 11. So we've got some relative max and relative min. The area is the regions bounded by the t-axis in the graph. Okay, they're on there. This one's 6. From 0 to 3, it's 6. 3 to 9, it's 9. 9 to 13, it's 3. And then 13 to 15, it's 2. So that paragraph is just describing what's happening. So for part A, it says for 0 to 15, find the time and position of the particle when the particle is furthest to the right. Justify your answer. Okay, so basically we want to figure out where it is when we change from right to left. Because you go right and then changing to left. So that happens in two different places. Because 0 to 3, we're going right. Because it's above the x-axis. And then 3 to 9, we're going left. 9 to 13, this is positive, we're going right. And then this little piece down here, we're going left. Okay, so right, left, right, left. All right, so it starts at 4. So our first one, we start at 4 and we change directions at 3. So S of 3 would equal 4, and then plus actually the integral from 0 to 3 of your velocity, which is just 4, and then plus 6. So that equals 10. So we end at 10 to the right. And then we go left. We actually go left 9. So we're actually going back to 1, because 10 minus 9 is 1. Then we're going to head right away again from 9 to 13. So S of 13 then would be 4 plus, and then our integral from 0 to 13. There is other ways to do this, but actually we'll explore that and be. So from 0 to 13 then, you have your 4, you would add 6, so right 6, left 9, and then you go right 3. So add all those together, you get 4. So find the time and position of the particle when it's furthest to the right. So it's furthest to the right when t is 0, because yeah, it's a 10. So we tested 0 to 3 and 0 to 13. Okay, I don't know what else to say for justifying there. All right, for how many values of t where 0 is less than t is less than 15 is the particle at x equals 4? Okay, this is where I'm going to consider the whole thing. So first of all, the function is continuous. So I'm setting myself to be able to use the intermediate value theorem. All right, so it starts at 4. There's 1 4. Okay, so it starts when x is 4, not the time is 4. So when t equals 0, x equals 4. And then from 0 to t, or 0 to 3, so 0 less than t less than 3, it goes right 6. Which means it ends at 10. Okay, so here's 1 4. All right, and then from 3, what's our next chunk? 3 to 9, it's going to go left 9, so it would end at 1. Then we're going 9 to 13. It's going right 3, so it would end at 4. Then we got one more. Then 13 to 15, it's going left So it ends at 2. Okay, that pretty much just describes what's going on. So the question is, for how many how many times is x equal 4? So x equals 4 right here. And then between 10 and 1, it would have to go through 4. Now I set myself up. That's using intermediate value theorem. That's why I said it was continuous. And then it's going to end at 4, so there's going to be one more. So using intermediate value theorem, it goes through 4 3 times. And that answers that question. Hopefully explain that so it makes sense. Alright, and then C says, at what intervals is the speed of the particle increasing? Give a reason for your answer. Alright, so speed of the particle increasing. Before we had decreasing, now we have increasing. These they have to match. So we need to have a positive going up. So the first little chunk is positive, but it's going down. Not it. So then we have going down negative. There we go. That matches. So we have from 3 to 6. That's it, yeah. From 3 to 6. Because velocity is negative. And acceleration is negative. Okay, so 3 to 6. Then we have positive, negative, not it. Then we have positive, positive. There we go. So from 9 to 11. So velocity and acceleration are positive. Sorry if I keep spelling acceleration wrong. All right, and then, so 9 to 11, and this is negative, but it's positive, not it. This is negative, and it's negative. So we have one more from 13 to 15. Because they're both positive. Negative, negative, negative. Okay. Okay, so speed is increasing, and they're the same. Well, there's acceleration right there. I am spelling it right. Okay. And last thing, during what time intervals, if any, is the acceleration of the particle positive? Justify your answer. So acceleration being positive is just where the graph is increasing, and it's only increasing on one little bit, and that's going from 6 to 11. Nothing with a 0. Because the velocity is increasing. All right, what a good review. I will assign homework inside of Teams. So your goal for today is mostly just get these notes down. They were pretty long. If you want to start on your homework, that's awesome. And on Thursday, we'll have another kind of question day, just like we did today or yesterday, whatever day it was. It's all blending together. All right, so stay safe, and I will talk to you all soon.